GWAZMATICS.
Welcome, ladies and gentlemen, to the debut production on GWAZMATICS. This is the branch of Gwaze tutorials whose videos I'll be posting on YouTube for free consumption. And the main thrust on this branch will be to teach you topics that are relevant to mathematics. Anything pertinent to O-level, A-level, even first year tertiary level courses in mathematics. Unlike the counterpart Gwaze-Nomics, which looks at economic topics, whether macro or micro in nature, Gwaze-Matics is solely or purely sanctioned on mathematical issues. Our topic will be on equations today. I won't be exhausting the whole curriculum on equations, but the sub-focus will be on simultaneous equations. By the end of this production, you must be able to identify a simple linear equation involving two unknowns. Solve a pair of linear equations simultaneously using the elimination method. Then verify your solutions from there. So each of these objectives will be met in turn as we proceed through this presentation. In meeting up with the requirements of the first objective, it is necessary for me to establish the definition of a linear equation before I continue with solving simultaneous equations. So, linear equations come in various forms, and one of the examples would be an equation of the form 3x plus 1 is equal to 7. So before I solve the equation, let's just identify the characteristics that qualify this equation as being a simple linear form. Well, the most important property of this equation that qualifies it as a simple linear equation is the power of the unknown. In this case, our unknown is x, and the power of the unknown is 1. So in any simple linear equation, the power of the unknown is 1. So that is just a simplified definition for a simple linear equation. There are many other forms of linear equations, those including bracketed expressions, fractional terms, or even fractional coefficients. But I've just chosen one of the simplest forms because the main focus is not on solving the equation, but we need to quickly move on to how we solve simultaneous equations. So this is just building up the background. So to solve this equation, we have to isolate x by removing positive 1 and 3. To remove the positive 1, would have to transfer it to the right-hand side of the equation, which is RHS in acronym form. So we are transferring it from the left-hand side, that is LHS in acronym form, to the right-hand side. And in doing so, you experience a sign change. Whenever you transfer a number or term from one side of the equation to another, the sign of that number or term changes. So hence your right hand side would develop onto 7 minus 1. Your left hand side will collapse to 3x. Further simplifying your right hand side, this will collapse to 6, and we still maintain 3x on our left hand side. Now, to remove the coefficient of x, that is the number attached to the unknown x, we'll just divide 3 into both the left hand side and the right hand side. And in doing so, x collapses to 3 divided into 6, which will give us 2. And that is how we go about solving a linear equation of this form. Alright. Now that we have identified how we define a simple linear equation and how we can also solve the simple linear equation, we can now make the transition onto solving simple linear equations involving more than one unknown. So suppose you have an equation like x minus y is equal to 10. Clearly you can see that this equation is now involving two unknowns instead of the previous case where we're solving for one unknown. And it complies with the properties of a linear equation in that each unknown has the power 1. Alright. I think you can agree with me that the format we've used to solve for x cannot be adopted in this case. We cannot find the value of x and y by using a single equation. So this is where the aspect of simultaneous equations comes into play. So we have to come up with or include another equation involving the same set of unknowns so that we can solve for the value of x and y from thereof. So that the other equation will be 3x plus y is equal to 6. There are many approaches involved in solving simultaneous equations. We can make use of the elimination method, substitution method, the matrix approach, and even the graphical method. But for this production, we are going to center our focus on applying the elimination method. So before doing so, let me just clear up the screen as we get started. So in working with the elimination method, I would like to apply the following example. The equation appearing on your screen is 3x minus y being equal to 4, accompanied by the second equation 4x plus y being equal to 10. So it is a prerequisite that if you are to find the value of two unknowns, you are supposed to have a pair of equations which will solve simultaneously or concurrently. The first step involved in the elimination method is to number each equation. Well, the bare reason for numbering each equation is just for identification purpose. It's like giving the equation a name so that we can identify with that equation throughout the process as we carry out the elimination method. Right? But let me mention at this juncture that this would not be your first step. If your equation started off in this form, say you had x is equal to y minus 9, and another equation, say another equation of the form y is equal to 3x minus 19. So if your equation started off with like terms, or say your unknowns scattered on different sides of the equation, you would have to rearrange the equations so that your algebraic terms, those are the terms containing the unknowns, are ordered on the left-hand side. Not only ordered on the left-hand side, but make sure that like terms are in line with each other. So your X bundle or X terms are in line with each other, and your Y bundle or your Y terms are in line with each other. Then you are supposed to arrange your numbers on the right-hand side. So clearly, the latter pair of equations does not comply with this format. So we have to rearrange our equation so that any of the unknowns on the right-hand side are transferred to the left-hand side. If you do so for the first equation, it will collapse to x minus y is equal to minus 9. Do the same for the other equation. This will collapse to, bearing in mind that the salient sign being positive, this changes positive 3 to negative 3x added to y, where the positive sign was a salient feature, is equal to minus 19. Alright, so that is how we develop the equations so that they can comply with this format. So that would be your first step. Given that your equations started off in this way, you would have to rearrange them. But otherwise, if your equations bear this format from the onset, then your step number 1 would be to number each equation. So in numbering our equations, 3x minus y is equal to 4 is our equation number 1. 4x plus y is equal to 10 is our equation number 2. The second step involved is to eliminate either x or y by equating the coefficients of the unknown to be eliminated. Before I proceed on explaining what this means, let me just conscientize you that it is at the beginning of step 2 that we start to appreciate what elimination is all about. I think you're asking, where does elimination fit into the picture? Well, the topic elimination is actually embodied initially by step number 2. So to eliminate is to remove, okay? We want to remove either x or y from the equation so that we can solve one unknown at a time. You get it? So we are going to eliminate or remove x or y. As I was developing this example, I chose x as my unknown of choice. You can choose y if you prefer y to eliminate y, but I chose x because there are a lot of aspects we are going to cover which will be very, very useful to you as you encounter other challenges pertinent to this topic in the future. So the sub-process under step number 2 is equating coefficients. The definition of equating, which I'm going to use in context of this topic, is to make the coefficients of x identical. So we have to make 3 and 4 identical. Alright, that is what I mean by equating the coefficients of x or the unknown to be eliminated. And how do we do so? Well, we start off by identifying the LCM of our coefficients. Pardoning the signs, of course, we have positive signs being salient there, but 3 and 4, we are going to consider them as absolute values for the purpose of identifying our LCM. So the LCM of 3 and 4 is 12. Why I've chosen to work with the lowest common multiple is just the aspect of simplifying our calculations. You can work with any common multiple, 24, 48, even if you prefer 96 billion. But the smaller the common multiple, the simpler the calculation. So that's the whole aspect behind working with our LCM. After identifying our LCM, we then find the quotient of that LCM and each initial coefficient. So the quotient of 12 and 3 will be 4. The quotient of 12 and 4 would be 3. Okay? Why are we coming up with these quotients? The reason is for us to transform equation 1 and equation 2, so that not only are we going to get identical coefficients for x, but we are going to transform all the other terms for the purpose of solving our two simultaneous equations. So in order to transform equation number 1, we are going to multiply it by its quotient 4. And in order to transform equation 2, we are going to multiply it with its quotient 3. The next sub-process under step number 2 is establishing a sign difference where 1 does not exist of the unknown to be eliminated. Allow me to underline a very important concept in this sub-process. We only apply this sub-process, which I am ticking, whenever there is no sign difference between the two coefficients. Those are the initial coefficients. So going back to the initial coefficients of x, we had positive 3 and positive 4. Clearly you can see that there is no sign difference between these two coefficients. They are both positive. But suppose if there was a sign difference, if one was negative and another was positive, then there would be no need to use this process. But because there is no sign difference, we are going to make use of that process. Now the question comes to, how do we establish the sign difference? Well, we have to manipulate the signs on either positive 3 or positive 4 by placing a negative sign on our quotients. So you are going to place your negative sign on 4 or on 3. I choose to place my negative sign on 4. And in placing our negative sign on 4, we can be able to manipulate our signs in order to establish a sign difference. So in transforming equation 1, we are no longer going to use just 4, but negative 4 to multiply each term in equation 1. So negative 4 times 3x will give us negative 12x. Negative 12 times negative y gives us positive 4y. Negative 4 multiplying 4 gives us negative 16. Don't worry, all these terms are neatly presented for you on the next slide. I'm just developing the background for what we'll be looking at in the future, in the near future. We do the same for equation 2. We are going to transform equation 2 by multiplying each term thereof by 3. And this will give us 12, or positive 12, where the positive sign is the salient feature, plus 3y being equal to 30, or positive 30, the salient positive sign being there. So this is what we carry out in compliance with step number 2. Okay? Equating our coefficients and establishing a sign difference. Before I depart from this part of the presentation, let me just say that if y was your unknown of choice, step number 2 would be unnecessary. Why? Because already as it is, the salient coefficients of y are already identical. We have 1 in each equation, being the coefficient of y. There is already a sign difference between the coefficients. So you wouldn't have to observe step number 2 if y was your coefficient of choice, or your unknown of choice for that matter. in reflection of what I've just developed from the previous slide, transforming equation 1 by multiplying each term thereof by -4 gives us equation 3. So equation 3 is just the transformed equivalent of equation 1. And equation 4 is the transformed equivalent of equation 2, having multiplied each term thereof by +3. The next step involved is to add up like terms in equation 3 and equation 4. Okay? So in doing so, we have to consider each bundle of like terms. So the first bundle is minus 12x plus 12x. And this will collapse to 0. You get it? Minus 12x plus 12x collapses to 0. And just at that process or that particular point, we have eliminated x. So you might have asked, why were we establishing a common or an identical coefficient for x, and why did we have to have a sign difference? All that process under step number 2 was aimed at eliminating x. Alright, so we're just aiming at removing x or neutralizing x. Right? Let's move on to the next bundle of like terms. Positive 4y plus 3y collapses to positive 7 with a salient positive sign being developed. Minus 16 plus 30, that's minus 16 plus 13 plus 30 gives us positive 14. I think you can appreciate at this juncture that this topic on directed numbers is a very important or integral part of simultaneous equations. If you don't have any assumed knowledge on this topic, please post some comments which I will entertain and develop the topic for you on directed numbers. But if you have no challenge at all on this topic, then let's continue. So we are going to solve for y. And in solving for y, as noted in step number 4, we are dividing the coefficient of y into both the left-hand side and the right-hand side. Y then collapses to 2. Now that we have obtained the value of y, let us move on to step number 5, which involves substituting y being equal to 2 into any of the 4 equations, equation 1, equation 2, 3, or 4. The purpose of carrying out step number 5 is to come up with the value of the other unknown, which is x. Alright, so you're wondering, now that we've got y, how do we come up with the value of x? Well, we just have to follow through step number 5 to get the value of x. So you're going to choose among the 4 equations the one that you opt to work with. My equation of choice is equation number 1. So let's just observe in retrospect what were the terms in equation 1, which are clearly defined here. 3x minus y is equal to 4. So let's work with equation 1, whose terms are 3x minus y is equivalent to 4. My question to you is, how do we use equation 1 to come up with the value of x? Can you just think about that for a minute? Well, as stated in step number 5, we are supposed to substitute y being equal to 2 into equation 1. So we are replacing y with its numerical equivalent. And in doing so, we develop the following equation. 3x minus 2 is equal to 4. Now that you have obtained an equation with x being the sole unknown, let's solve for this equation. You can carry out the process on your own. If you manage to get the idea of solving a simple linear equation involving one unknown, the one that I illustrated at the beginning of this production. So as you remember, that would involve transferring negative 2 to the right hand side, so that 2 adds up with 4, and the equation collapses to, as we solve for x, as highlighted in step number 6, the equation collapses to 3x is equal to 6. We then divide out the coefficient of x into both the left hand side and the right hand side, so that x becomes equivalent to 2. So this is how we carry out the elimination method, boys and girls. It's quite a mouthful, but if you are to revise all the procedures over and over again, I think you become a maestro in this area. Before I depart from this part of the presentation, let us now go on to meeting the requirements for the last objective, verifying our solutions. Now the question is 2 the accurate value of x, and is 2 the accurate value of y? Well, in order to verify our solutions, we have to carry out the following procedure, which is not necessary under examination conditions, but if you want to be more prudent with your solutions, then I'll advise you to carry out this procedure. So what we have to do is to plug in the value of x and y into either equation 1, 2, 3, 4. And if these solutions are indeed correct, the answer that you obtain on your left hand side in any equation of your choice should be equivalent to the answer you obtain on your right hand side, which of course upholds the basic law of equations. Your right hand side should be equivalent to your left hand side. So my equation of choice will still remain with equation 1, and I'll plug in the numerical equivalent of x and y in this equation to give 3 multiplying 2 minus 2 being equal to 4. I'll append the question mark since we have not yet verified whether this aspect is proved. 3 multiplying 2 is 6, less 2 gives us 4. So since our left hand side is identical or equivalent to our right hand side, we can safely conclude that these numerical values of x and y are indeed correct. So before concluding this production, carry out the following practice item. Solve the following pair of simultaneous equations using the elimination method. So your unknowns are a and b in this case, right? So you just choose whichever of the 2 unknowns you want to work with and try to apply the procedures I outlined in the example to this practice item. When you're through, you can resume the video and check whether your solution tallies with mine. Welcome back. Let us explore whether you made some significant progress or not. So the solution is laid out as follows. You number each equation since the format I once outlined is already given. So the first step would be to number each equation. All right. Having numbered each equation, you are going to eliminate the unknown of your choice. The unknown of my choice, I wouldn't know about you, but don't worry, whichever unknown you have chosen, our answers will still tally. So my unknown of choice is A. Since the coefficients are different, I'll have to identify the LCM. And the LCM of 4 and 13 the absolute LCM is 52. Okay. So the quotients thereof, 4 into 52 gives 13. And 13 into 52 gives, ignoring or pardoning the signs, by the way, we are just looking at absolute quotients. 13 into 52 gives 4. Okay. Now we transform each equation by multiplying them by their respective quotients. Please observe how we are not going to manipulate the signs, since we already have a sign difference. One coefficient is positive, the other is negative. So there is no need for us to manipulate the signs. All we have to do is to establish identical coefficients, or to equate our coefficients. So in transforming equation 1, we get equation 3. In transforming equation 4, we get equation, that is in transforming equation 2, by multiplying each term thereof by 4, we get equation 4. We add up our like terms. 52a less 52a collapses to 0, hence we've just eliminated a, and after attending to the other cluster of like terms, the equation will collapse to 9b is equal to 171. Let's solve this equation. So dividing 9 into both the left hand side and the right hand side, b will collapse to 19. Substituting b is equal to 19 into any of the 4 equations, equation 1, 2, 3, or 4. My equation of choice is equation 1. Remember, whichever equation you used, still our answers would tally. So this would develop to 4a plus 19. Notice how I've used the original, or I've just transformed some of the original terms in equation 1, your equation 1 right here, which were 4a plus b is equal to 11. And how I plugged in the numerical equivalent of b to occupy the position of b in equation 1. Hence, we end up with this equation. In solving for this equation, we have 19 being transferred to the right hand side, so we end up with negative 19, and 11 minus 19 collapses to minus 8. Dividing the coefficient of a into both sides of our equation, that is 4, a collapses to minus 2. The golden question is, are these two numerical values of our knowns correct? Is a indeed equal to minus 2 and is b indeed equal to 19? Well, let's make use of any equation of our choice to verify our solution. I'll stick with equation 1. So plugging in the numerical equivalents of each unknown will lead us to 4 multiplying minus 2 plus 19. And the question is, will this collapse to 11? That's the question appended on our equal sign. We have not yet validated it as yet. So 4 multiplying minus 2 gives us minus 8, added to 19, which gives us 11. Does it? Well, we are still on the process of validating, so the question mark is still relevant. So minus 8 plus 19 does indeed give us 11. Hence, we have just validated the solutions of A and B. That brings us to the end of the debut production on Gwaze-Matics, which was focusing on solving simultaneous equations, which are linear, simple linear equations in nature, and how we apply the elimination method to solve for the unknowns. And it's also important to verify your solution if you still have time in the examination. But this procedure is not necessary when you become more and more confident with yourself. But as you develop as a new student to this topic, I advise you through your practice schedules to always verify your solution so that you develop enough stamina. So that brings us to the end of the production. Keeping in touch, those are the communication platforms appearing on the screen. Mr. Gwaze, that's me. My business partner, Mr. Masiachengo. His area of speciality will be in teaching you accounting and business studies topics. So watch out for those. Till we meet, may the grace of all time be with you in Jesus' name. So God bless you. And remember, as declared by Luke chapter 1 verse 37, with Jesus Christ, our Lord and Savior, no declaration is an impossibility. So to the viewers all over our beautiful globe which God gave us, whether in Africa, America, Asia, Australia, Europe, or even the Saudi Arabian belt, whichever part of the planet you come from, may the grace of all time be with you. And please stay in good shape and know that God loves you. So till we meet, God bless.